Alright, so this video we're going to start talking about chapter 12, and specifically in this section 12.1 we're going to talk about exponential functions. Now exponential functions are very important to mathematics because there's many real phenomena that we can see in the world around us that can be modeled with exponential functions. We have things like exponential growth, compounding interest. And so these models will become very important. Now exponents are nothing new to anybody that studied mathematics. We've seen exponents before. They're things that have this form b to the x, where we have a base and we have a power. Now the only thing that's different about an exponential function is now we say, okay, well f of x equals that b to the x. We also require that the base b that we're raising the power to is a positive number, and that it's any positive number except for 1. And anytime we have that, then we have what's called an exponential function. Now, one thing to point out is that the variable is the power, or the exponent. So when we're plugging in an x, that power, that x, goes into the power. Now, right below here we have some examples of exponential functions. Notice that in each one of these examples, the x is in the power. You will always see that in an exponential function. Notice they all have f of x. Now the bases change. We have 3, we have 25, we have 2/5, we have 5, we have 4. We can have different bases as long as they're positive and not equal to 1, which none of these examples are. The x has to be in the power though. So one of the first things we'll do is you have to be able to evaluate a function. So we should all be comfortable doing this with exponential functions because it's the same exact concept as if we don't have an exponential function. If we want to find f of 5, that means we're going to put 5 in for x. So this is going to be 3 times 2 raised to the 5 minus 4 plus 29. And we simplify the power first, so 5 minus 4 is 1, so this is going to be equal to 3 times 2 to the first power plus 29. Of course, 2 to the first power is just 2, so this is 3 times 2, or 6, plus 29, which equals 35. So we just found that f of 5 is equal to 35. Or for this particular function, when the input's 5, the output is 35. I also have some examples here of some different graphs of exponential functions. And I want you to just take a moment and look at these 4 graphs that represent these 4 different functions outlined above the graphs, and just kind of compare and contrast them. What do you notice that's the same? What do you notice that's different? And go ahead and think about that for just a moment. Okay, so what are some things that are the same? Well, we should all notice that they all have the same y-intercept point. They all go through this point, the point 0, 1. They all have that point, right? They all have the same y-intercept. Now, and that should make sense, because if you put your power to 0, 3 to the 0 is 1, 25 to the 0 is 1, 2/5 to the 0, and 5 to the 0. No matter what the base is, anytime you raise something to the 0 power, the output is 1. Now, one thing that's different is these first two, the graph is climbing, it's increasing. it's increasing. And then in the second two graphs, the line is decreasing from left to right. It's decreasing. And notice what's different. Here we have base 3, base 25. Here we have a fraction base. And in the second one, we really have a fraction base too, because if you recall, remember how we turn something into a positive exponent? We move it to the denominator. So I could really say that this is the same as 1/5 to the positive x. So it's a fractional base as well, and that's why it is decreasing like the third example. So I pose a few questions here. The first question is, what do you think the domain is for these exponential functions? And you could look at the graph like we looked at all semester. We could also just ask ourselves, is there any limits on what these x values can be in the powers? Is there an x value that I can't plug in? And of course the answer to that is no. You can plug in any x. And that's why we see this graph continuing off to the left and also continuing up and to the right. It's going to cover all our x values, which means the domain is everything from negative infinity to positive infinity. What about the range? Is it all the y values? Well, it doesn't look like it. It looks like with all these graphs down here as we go to the left, it looks like it's the y values are kind of getting close to 0. Same thing in the second graph, they're getting close to 0. Same thing even the last two. As we come down here to the right, the y values are getting close to a y value of 0. Y values are coming down, they're getting very, very close to 0. So might be like 0 and up, maybe everything from 0 to infinity. Does it actually ever equal 0? Well, I guess the question you have to ask here is there 3 that I can raise to any power and ever get 0? Is that possible? And I think you can come to the conclusion that no, that is not possible. I can get really, really small, but I can never actually approach 0. And this is where this idea of what we call a horizontal asymptote comes in. A horizontal asymptote, let's write this in, is a horizontal line horizontal line that a graph gets really close to, but does not touch as x gets really big in both the positive and negative directions. So we can say as it goes towards infinity or negative infinity, as x gets really big in either direction. And so what we really have here is we have, let me draw it in red here, we have this horizontal asymptote here. I'm going to draw it as a dashed line. Usually asymptotes are drawn in red. We have it on all four graphs. We have the same horizontal asymptote. The equation of these lines, as we have learned, the equation of that line has got to be y equals 0 in all of these. Y equals 0. Y equals 0. This is a horizontal asymptote. In other words, my graph is getting really, really, really close to that red line, but never touching it. And so the domain, the range. The range is all the y values bigger than 0. So 0 to infinity. But do we include 0? No. And so we're going to actually put a parenthesis there because we're never actually can be equal to 0. We just get really, really close to it. And so one little important note here that we saw in our first two graphs, graph 1 and graph 2. This is where the graph's going up from left to right. We had the case where the base, for both those examples, the base was, and the first one was 3 and the second one is 25. If the base is greater than 1, which both 3 and 25 are, 3 here and 25 here, the base is greater than 1, then f of x equals b to the x will be an increasing function. It will get bigger, the y values will get bigger from left to right. And so let's take a look at graphing one of these. Let's take, for example, the function f of x equals 2 to the x. And let's pick some x values that are easy to calculate. I'm going to make a little table here. We have x, and we have f of x equals 2 to the x. So if we take three different inputs, -1, 0, and +1, then that first one will give me 2 to the -1. We know that negative exponents cause us to move down to the denominator, so this will be 1 over 2, or 1/2. Next one is 2 to the 0 power. Anything raised to the 0 power is 1. And then if the power is 1, that's 2 to the first power, which is 2. We could do a couple more here, just to kind of get an idea here. If the input is 2, it's 2 to the second power, which is 4. Oh, and 3. How about 2 to the third power? That is 8. So a couple points. The first couple points we had was when x is -1, y is 1/2. When x is 0, y is 1. That's that same y-intercept that we always see, 0, 1. And the last one, when x is 1, y is 2. And so we can go ahead and put these points on the graph and see that the shape should be the same sort of shape as what we saw in the graphs on the previous page. Let's go ahead and put those in there. So first, the point -1, 1/2 is right about there. The point 0, 1. We have the point 1, 2. Point 2, 4. And 3, 8. And you can see again we have the same shape like we had in the graphs on the previous page. It doesn't take very long for as x gets bigger, the y values get bigger even faster. And so this is why sometimes you may hear the terminology exponential growth. Exponential growth is called growth that's really fast. That means the y values get big really, really quickly. And so the domain of this, just like on the last page, we see that this covers all the x's. Domain is -infinity to infinity. And the range, again, in this case, is everything from 0 to infinity. And we don't put a bracket on 0 because we're not going to include 0. Remember, there's that horizontal asymptote here. That the graph gets really, really close to y equals 0, the horizontal asymptote. Graph gets really, really close to it, but it never touches it. Okay, so there's one example. Now, based on our examples in the previous page, do we have an idea of what this is going to look like? We have a base of 1/4. Remember that in that case, that's where we have like the third and fourth graphs on the previous page. The line, when we have a fraction, goes down from left to right. Now let's see why that is by plugging in some points. If I again make a little table here, choose some inputs, x, and then we have f of x equals 1/4 to the x. We can see that when we plug in -1, this makes 1/4 to the -1. And remember, to turn that into a positive power, it makes it 4/1 to the +1, or just 4 to the 1, or 4. So we have -1, then y is 4. And then we have 0, that's 1/4 to the 0 power, which is 1. And then the third point is 1/4 to the first power, which is just 1/4. Again, we can put these guys on the graph. Okay, so first point, we have -1, 4. We have 0, 1. And we have 1, 1/4. And we could do some more points, but you can see this is going to continue down here, and these y values are going to get really, really small. They get really, really close to 0, but they'll never actually be equal to 0. One of the things we haven't done yet is talked about graphing these with a graphing calculator. So if we were to put this in our graphing calculator, we go parentheses 1 divided by 4 raised to the x power, and hit our graph here. And you can see that's basically the shape we got. We can look at our table. Notice as x gets negative, these numbers get really, really, really big. And then at 0 we have 1, and then as x starts to get further positive, our y values get really, really small. Even down here, 5 and 6, this is scientific notation. This is 9.8 times 10 to the -4th power. And so if the last example was what we call an increasing function, when the base is a number bigger than 1, here we have a fraction as our base, 1/4. We call this a decreasing function. When the base is less than 1, we get a decreasing function. Domain is still -infinity to infinity. The range is still everything from 0 to infinity, but this one is decreasing instead of increasing. So this would be an example of what we call exponential decay. Exponential decay. The values are getting smaller, whereas the last example might be an example of exponential growth. Things are getting bigger really quickly. And so one of the numbers that we see show up a lot as a base for an exponent is the number e. We define it as the letter e, and it's called the natural base. E is called the natural base, and it's the number 2.718281, and it just keeps going on and on and on. It is, if we use that in our function, then we're just basically taking our f of x equals b to the x. Remember, that was how we defined an exponential function. And we're letting the base equal e, which makes it f of x equals e to the x. And if we have f of x equals e to the x, we call it the natural exponential function. And there's a button on the calculator for that. It's just above your ln button. And so we could use the calculator to help us find things like f of 2. So if we wanted to find f of 2, that's going to be e raised to the second power. And if we wanted to find f of negative 3, that would be e raised to the negative 3 power. And let's use our calculator to help us with what both of those approximations are equal to. So if we pull up our calculator, we can take a look at e to the second power. Well, the 4 decimal place, that is about 7.3891. 7.3891. Again, to find that e to any power, we got to hit second before we hit ln to get the e. And then likewise, we could find e to the negative 3 power, and that's going to be 0.0498. This is about 0.0498. And that'll do it. Thank you. What do you think the graph of f of x equals e to the x looks like? Well, it's basically the same shape as the other exponential functions we've already graphed. If I even put it in my graphing calculator, y equals, let's clear out the old function and let's now put in e to the x second e to the x and hit graph. Should be exactly what you expected. It's an increasing function. Remember, e is the number 2.7182818, blah, blah, blah. That's a number that's bigger than 1, which means it's an increasing function. If I look at my table, as x gets big, the y values get big fast. It's exponential growth. So this particular function looks just like the other ones. Has a y-intercept at 0, 1, and so on. Now, how do we solve these? We're going to look at solving different ones throughout this chapter, but we're going to start off with just a basic idea, and that is when we have an exponential equation, the variables in the exponent. Can you see that this is really easy to see what the answer is? Well, in this case, it's even easier because we know that 3, of course, squared equals 9. But one way to see this is to write both sides of the equation with the same base. So if the left-hand side is 3 to the x, of course, we can write the right-hand side as 3 to the second power, because 3 squared equals 9. And if that's the case, then that means that x has to equal 2. We can set the bases equal to each other. And so that's why I say in the question down below here, can you see that if we can write both sides in terms of the same base, in this example it's base 3, then the exponents must be equal. For example, in example A, we have 7 to the x plus 4, and we know that 49 can be written as 7 squared. Right? 7 squared is 49, so if we can rewrite it like that, then that means that the powers have to be equal. It means that x plus 4 on the left-hand side has to be equal to 2. And if we go ahead and subtract 4 from both sides, that means that x has to be equal to a negative 2. Hopefully that makes sense. Likewise, we can do the same thing in the next problem. We have Both sides can be written as 2 to some power. Left hand side we have 2 to the 3x minus 2, but on the right hand side 128 is the same as 2 to the 7th power. So, and if you're not sure about that right off the bat, you can just start guessing things. Maybe you think it might be 2 to the 6th. Well, it's not 2 to the 6th, but if I multiply 64 times 2 once more, so 2 to the 7th power, we can see that's equal to 128. And once we have the bases the same, both in base 2, then we just like the last two examples, we set the powers equal to each other. So 3x minus 2 has got to equal 7, which if we add 2 over the other side, right, add 2, we end up getting 3x equals 9. And we divide both sides by 3, we get x equals 3. Now, the next two are not quite as obvious, but still, I don't think too bad. We have 25 to the x and we have 1/5. Well, hopefully you can notice that they can both be written as 5 to some power, because 25 is 5 squared, and of course that's still risen to the x power, and 1/5 is 5 to the negative 1 power. 5 to the negative 1 power. Negative exponents cause the fraction to move or flip over. On the left hand side here, we're raising a power to a power. 5 squared raised to the x power, we multiply the power, so this is 5 to the 2x equals 5 to the negative 1. And now notice we have the same base. That means the powers must be equal, which in order to get x by itself we have to divide by 2. This means x has got to be a negative 1/2. And then the last one, we have 8 to the x minus 7. This seems maybe impossible at first, but remember that anything raised to the 0 power is 1. So this is 8 to the 0 power is equal to 1, which means the left-hand power has got to equal the right-hand power, which means after adding 7 to both sides, x has got to be 7. So this is how we go ahead and solve exponential equations. We'll round up this section by doing an application of an exponential function. We talked before about exponentials representing or being used in real-world applications. One of those is population growth, because typically populations can grow exponentially. So we have an example here where it says the population of a particular small town can be approximated by the function 350,000 times e to the 0.02x, where x represents the number of years after 2000. What will the population be in 2015? Well, the key to that is we got to know that 2015 is 15 years after what year? The year 2000. Which means if I want to figure out the population in 2015, I need to know what f of 15 is. And we're just plugging in. This is 350,000 times e to the 0.02 times 15. And everybody should be able to calculate this with your graphing calculator. Let's see how you would plug that in. We'd take our 350,000 first, and then we would multiply that by e. We know how to put e in there. And in the power we have 0.02 times 15. 0.02 times 15. Close the parentheses after that multiplication, that product of 0.02 times 15. And we get a new population. Now, anytime we're talking about a population, we're not going to want to give decimal answers. So we could round this up to 472,451. This is about equal to 472,451 people in the year 2015. Right? So that does it for section 12.1. You should now be able to do your self-check. I will see you in class. Thank you.